So good afternoon. I think we may start this lecture. I see the room well populated. This makes me happy. Just because I think the lecture we are having today is an extremely interesting topic with a very top-level speaker, and I think it is our duty to welcome this speaker in the way that he deserves. So let's say today we are having our third distinguished lecture. We have 3 of these this year, so this is the one that complete our program. It is something that we really believe it is very important for our department to have this kind of lectures that open our mind, open our vision. And so I believe this lecture will be exactly in this direction. We have a Professor Wolfram Burgard from the University of Freiburg, and I think the speaker today, I'm very happy to introduce him. He's working the artificial intelligence on mobile robots, especially in the development of robust and adaptive technique for state estimation and control. Over the past year, he developed a series of innovative probabilistic technique for robot navigation and control. He's a president of the IEEE Robotic and Automation Society. Not only he is within the Department of Computer Science of the University of Freiburg, but in the coming months, he will be the director of the Toyota autonomous and drive system in Palo Alto. So this, I think, is also very prestigious things. More than this, Wolfgang has the Gottfried Wilhelm Leibniz Prize in 2009, who is the most prestigious research, let's say, grant research award in Germany. In 2010, he also received an advanced grant for the European Research Council. So he is also owner of one ERC that we know very well is not an easy task to get. So congratulations for this as well. Looking to his citation number, you are astonished because he has an H-index who is larger than 100. He has a total citation of 60,000, kind of more than 5,000 citations per year in the last 5 years. So it is indeed a sign that the speaker today is very good. So it is my honor and pleasure to welcome Professor Wolfram Burgard to give this lecture. Thank you very much.
So sound check, I guess you can all hear me. Thanks for inviting me. It's a great pleasure to be here. It's my first time in this beautiful city that I didn't know is that nice, and I enjoyed it a lot last night and also this morning when I walked here from the hotel. And yeah, it's a great pleasure to be here and talk a little bit about the research that we have been doing in the past and also how this transitioned a little bit over the past years. And what I expect is going to happen in the near future with all these technology that we are going to discuss in the next approximately 45 to 50 minutes. What I'm going to start with is a metaphor that I'm going to use throughout this presentation. It actually comes from Greek mythology. This is a poor guy called Sisyphus who was condemned by Zeus because he believed that he's more intelligent than Zeus, that he was condemned to actually carry a big boulder up a steep mountain. And the problem was whenever he was close to reaching the top of that mountain, Zeus made the boulder run down the hill again, and he had to start from scratch. You now might wonder what that does have to do with science, and here is the parallelism. So you can imagine like us being this poor guy, right? So here, us, right? Having to carry out the boulder up a hill, which is a big problem, right? And once we are almost close to solving that problem, we discover, oh no, that's not going to make it, right? And then all of a sudden, this boulder rolls down the hill and you have to start from scratch with another approach to solve that problem. We will come to that throughout this talk, and I will give you an example of how that actually happened to me in this area of mobile robotics that we are working in. And what I want to look particularly at is this problem of mobile robot navigation. And if you look at this, then you can roughly subdivide the robot navigation landscape into 3 major problems. One of them being that of localization, answering that question, where am I? The next one is that of robot mapping, like what does the environment look like? And the third one is that question of like control, like how do I actually get from A to B? And in fact, there are all kinds of overlapping areas in that as well. Like, for example, when you speak about like the overlapping area of localization and motion control, there's one topic that is called active localization. Where should I look next in order to figure out where I am? Well, it's something that like intersects motion control and state estimation in this context. And there's also exploration. When you think about a rover on Mars, that what it needs to do is it needs to actually generate actions that allow it to acquire as much information as possible. That is what is called exploration. And then there's also the overlapping area of mapping and localization, one of the most active fields in mobile robotics over the past 15 to 20 years, which is called SLAM, standing for simultaneous localization and mapping. We will come to this in a second. If you look at the landscape, and this is my personal view, I forgot to mention there's also the most difficult area in the very center that does all the three things at the very same time. We don't have a cool name for this, but we are working on this as well. So this is my assessment of how good we are in these individual problems, and maybe also the overlapping areas, and do not know how big the scale is as to whether it's open-ended or as to whether there are 5 stars that end it. But I think we have made enormous progress in several of the approaches that also led to industrial applications. And this is something that we see right now, particularly when we look at what is going on in Silicon Valley. We are trying to cope with this or catch up in Europe as well, but we are lagging somewhat behind. And this is also another message of this talk, that we actually need to do something in Europe in order to keep the pace with what is going on right now in the United States and also in China, for example. So here's the very first example for this, and there's a little bit sound behind this, so you will hear some sound. You only need to focus on the very first sentence. Right? Let's see as to whether it works.
For a vehicle to drive itself, it needs to know where it is in the world, and it also needs to know what's around it.
So this is basically what captures the essence of self-driving cars. This is the former company, or the owner of that former company, or the owner of the self-driving car endeavor of Google. Like was Google itself, now it's Waymo. But in fact, what these people are working on is this problem of figuring out where the car is in the world. Localization, where am I? And this is super important simply because when the car knows where it is, then several things become easier. Right? For example, you know as to whether you can make a right turn or need to make a right turn. And also when you know exactly where you are, you can easily figure out where the traffic light is. And then the detection of the status of the traffic light is much easier when you exactly can cut it out from the image, rather than when you have to actually search for the traffic light in the image and maybe find the one that is corresponding to the lane of the car. So things become much easier when you, for example, know where the vehicle is. This is one example. There are other problems that need to be solved. But I want to focus on this navigation problem, and also like with a few words on object recognition as well. In fact, you need to know what objects are around in the world, and there's also something that we have been working on in robotics over the past years. So, but this entire problem is also relevant to other areas, like, for example, production or logistics. And that what we observe in industry right now are basically 2 ways of producing things mostly. Right? One is the fully automated way of, for example, assembly lines producing cars, where we are enormously fast but very, very inflexible. Right? On the other hand, we have the manual production, where we are like very, very flexible but very, very slow. And the idea now is to basically use the navigation capabilities of vehicles to achieve what is called transformable production, where we can have actually factories reconfigure themselves depending on the object that currently needs to be produced and manufactured. And this is one of the ideas, or one of the reasons why so many companies are working on navigation solutions for logistics, but also for assembly, because they simply want to make the assembly or the production sites more flexible and more effective by these type of approaches. And here's and this is one of the 2 examples why this is so super important. There are a couple of key challenges in navigation. And I want to talk about those in this presentation here. One is localization, and companies typically want to have this super accurately. Robust mapping, right? In order to localize vehicles need maps, and this is also something that we have been working on in the past. And then they also are interested in that what is called long-term autonomy. If you want to deploy a vehicle, then actually what you would like to maximize is mean time between failure, which means you want to have that what is called long-term autonomy. And I'm going to talk about those aspects in a little bit more detail throughout the next 15 minutes. So these are the key questions or the key aspects that I'm going to discuss in the first half of this presentation here. And for localization, if we look at that what is behind it, and turns out robotics has a lot to do with math. So you actually, if you want to study robotics or computer science or artificial intelligence, then that what you need to look at is mathematics, because most of the problems can nicely be described using math. And the same happens also for localization. And just to give you an intuition, that is what is behind localization, right? This is an equation that basically describes a famous algorithm, the so-called recursive Bayes filter algorithm, that estimates in a probabilistic fashion the state of the system based on observations and controls. So the robot moves based on the controls that we give to it, and it perceives the world, or it generates and it perceives the world using its sensors. And that what you would like to do is estimate where the vehicle is based on its perceptions, actions, and the map that it has in its memory. And basically what this equation does, it maintains a probabilistic belief about about the position of the vehicle. This is what is underlying like most of the state estimation processes in nowadays cars. So whenever you have an autonomous car, then actually it implements this equation over here in its core state estimator. And just to give you an intuition about one potential application of this, this is a robot that is supposed to localize itself based on ultrasound sensors, 24 ultrasound sensors in this case. And the idea of this algorithm, which is called Monte Carlo localization or particle filter-based localization, the idea there is to have a set of hypotheses, in this case 10,000, which is indicated or which are indicated by these red dots over here. The grayish one, the grayish areas, or the map, white is free space, gray is obstacles, and these blue lines are the measurements, the ultrasound measurements. Most of you have them in your bumpers in the car. That's actually the very same sensors that measure distances to nearby obstacles. And these are the returns from those sensors. And based on sequences of such observations, the vehicle needs to figure out where it is. The trajectory that the robot took was this one over here. The environment is a little bit complicated because it is actually symmetric in various ways. So because the doorways always look the same, the robot never exactly knows in front of which doorway it is, unless it reaches the end of the corridor. But then also it is rotationally symmetric, so it never knows as to whether it's facing west or east. And this ambiguity can only be resolved after entering this room or comparing this room to that room down here. And this nicely comes out of this probabilistic formulation and out of the math that you have seen just a second before. And what this algorithm does is it provides these hypotheses with the so-called importance weights that tell how much they fit to the observations of the vehicle and the predictions from the control. And then lets those hypotheses survive in a survival of the fittest manner, proportional to their importance weights. And this is the algorithm showing, or this is a video showing the algorithm at work. Right? So after a few seconds, like we see clusters of hypotheses in front of doorways, like relative to the doorways, all is the same. Then when a robot sees the end of the corridor, mostly two clusters survive, because from there only the robot can see the end of the corridor. And as soon as it enters this room over here, this cluster dies out because it looks different. The room looks much different from this room, so that the robot can actually differentiate between or disambiguate the situation. All right, so this is one approach for doing this. There are other representations as well, but this is basically something that has revolutionized robotics in the sense that based on this probabilistic formulations, we were able to build robot systems that can robustly localize themselves over long periods of time. The question now is, how accurate can you get by this? And this is something that is super relevant for industry. And so this is a study that we did a few years ago with some of my students, where we implemented this algorithm, enhanced it by a so-called scan matching algorithm for fine-grained positioning. And that what you see in this video is a robot performing a repetitive task. And you can imagine this as being a robot navigating towards a workbench. And the goal of this robot is to stop at the very same location at every point in time. So the robot actually goes back to a random starting point and goes to a random starting point and then tries to get back to that workbench and being as accurate as possible. We also left a few marks on, or put a few marks on the ground, but not for the robot to localize itself. It does this using those laser scanners. Over here, there's 2 of those. These black marks are only there for showing you the accuracy of the localization process. So and if you see, this is an omnidirectional robot. And as you can see here, the robot actually gets very, very nicely or close to that black spot on the ground. Right? This is this camera over here. And then when we repeat this, it actually turns out that it looks almost the same at the place where it gets to. The interesting aspect here was that it was the very first time that we needed to distinguish between localization and positioning accuracy, because the hardware was less accurate than our state estimator. So every hardware has some kind of a threshold. When you give it a command to move a quarter of a millimeter, then it typically doesn't do this anymore. So the robot didn't move anymore, but we knew exactly that the robot was half a millimeter off, but we couldn't control the robot to actually correct this. So and here are a few more experiments that we did. This is a collaboration with KUKA, a big German robotics company. And in this case, we used this 11-ton vehicle for navigating in a somewhat dynamic environment, where also we put so the lasers are here at the bottom, and we modified the environment by adding these obstacles over here in random fashions. We walked around also there. You can see that the positioning accuracy of this vehicle is in the order of 1 millimeter, and it goes slightly up in the case of dynamic environments. And the rotational accuracy is enormously high in this case. And this actually led to a real-world application, because it was sufficiently accurate for companies for building real-world applications with this. KUKA at that time built an application for Boeing, and where they transport the fuselage of the 777 through the construction sites in Seattle using a chain of these robots, and they also use that for bolting processes, where you do have 2 robots, one inside, the other one outside the fuselage, in order to actually put bolts, the 2 parts of the bolts together. And for this, you need highly accurate positioning of the vehicles. So this is one of the applications that you can achieve using highly accurate localization processes. But for this, you actually typically need what is called a map, and a highly accurate map as well. And I want to briefly talk about mapping, what has happened in robot mapping in the past. So this basically is that the overlapping area between localization and mapping, which the problem is called the so-called SLAM problem. So we are going towards robust mapping in the very next step. So the idea of mapping, of SLAM, that is what is called simultaneous localization and mapping, is to put the robot into an unknown environment, let it move around, and then use the data it gathered to calculate an accurate map. So this is similar to the problem when you are getting into a new city. Usually what you do is, unless you rely on your smartphone, you go to the front desk of the hotel and ask for a map that shows you all the streets around and all the landscapes that you're supposed to visit. Right? And now imagine those this hotel ran out of maps, and also the battery of your phone is drained, so you have to rely on your brain. But then all of a sudden it gets enormously complicated to get around, navigate through the city, and find your way back home. And this is basically what is behind the SLAM problem. So we expect the robots to collect data and to figure out what the environment looks like, and at the same time figure out where they are in this map. And this is the so-called SLAM problem. And one famous formulation of the SLAM problem is the so-called graph-based representation. So now let's look at this figure on the right over here. So what we see here is this black line over here is nothing else but a trajectory or path taken by a robot. that what you see around is data gathered with laser range scanners. White means free space, black means obstacles. So like when the robot just moves around here, everything looks fine. But then sometimes things happen like that the robot revisits places, right? Because usually the only thing you can do is relying on the wheel turns that the robot does. Then you basically need to do some basic geometry. Unfortunately, the world is not perfect. There are no perfect wheels, which means that you do have to cope with errors coming from like measurement errors in the odometry. Which then means that you get displacements of your trajectory from the previous like recording, And this can be substantial. Like for example, here we have a substantial error about like 20 degrees or 25 degrees whatsoever. But from the map here, or from the measurements, we can see that this actually looks like being the very same place. And once we decide that this is the very same place, when we do something that we call data association. So, and these type of data association now introduce that what we call constraints. Right? You can imagine this as a force that drags this spot over here to that spot over here. Right? So basically that means that link that you see here basically tells, I have two observations that look exactly the same, right? And if this is truly the same place, then the displacement of those two places must be that line over here. On the other hand, we have these odometry measurements, which tell like how far the robot moved based on its like wheel turns. Right? This also is some sort of a constraint. It gives us a prior about how far the robot moved between two observations of these wheel turns. And all these tend out to be that what we call constraints. You can also imagine this as being a big spring mass system where the poses, where you do observe measurement, odometry or laser, it's nothing else but a mass. And these connections or the data associations or odometry measurements are springs between the masses. And having this observation over here, from which we say this is very same, that introduces a spring, right, that is basically stretched out very, very far, and which introduces a force onto these masses. And that turns out to be that what we call a spring mass system. That's basically that what we calculate from the data that we gather. Right? And so we take these observations and calculate this graph that you see here that is nothing else but a spring mass system. Right? Then we throw away the data, and we are left with this graph or with this spring mass system. What we do now is, like physically, we throw this spring mass system into a bath of oil, right? Which means that somehow, that is known from physics, the system tries to reach a minimum energy configuration. Right? Like springs stretch further away will stretch springs like less stretched. And this is kind of like that what is happening. It goes into a minimum mass configuration. And the hope is that this is not only a local minimum, but also a global minimum, and the oil is necessary in order to actually make this process terminate, so that at one point in time, it actually stops. All right, so what we do is we basically move this, or move all these springs, or convert them into a minimum energy configuration, which is nothing else mathematically than least squares optimization. And you can also, when you look back at this probabilistic formulation, and this is nothing else but calculating the maximum likelihood configuration of the graph. And once we have this, we can use the data again and render the map again, and out of this, we get a nicely calculated map. And this is something that has happened over the past 15 to 20 years, where we in robotics developed these type of approaches. Many colleagues and also our group worked on this. And just to give you an intuition how robust this is, I have a short video here that shows that what is called sparse bundle adjustment, sparse post adjustment. It's a variant of bundle adjustment. Actually, it's a joint work with Kurt Knowledge and my students. And here you can see a couple of applications of this. So you basically see in the very beginning the graph being constructed while the robot is moving. Now we get a loop closure. And then you always see the optimization process where you see the map being corrected. You can also do this in a batch fashion when you actually calculate the graph in one, as we saw before, and then it gets corrected, but it can also go wild. Initialize everything with 0, 0, random orientation, And then when you're lucky, like the spring mass system gets unfolded into the correct path. And this is actually what has happened in robotics over the past years. And this is why now people say, okay, we have reached a situation where we can robustly build maps of the environment. By the way, all the map providers that you have on your cell phone use exactly this algorithm to basically gather to build the map that you have in your cell phone from the data gathered with their cars. So this is actually a variant of this algorithm. And might now ask the question, can we also do this in 3D, right? And this map wouldn't, or this slide wouldn't be here if the answer were no. Right? So in fact, can also do this in 3D, and this is just because it's a cool visualization data set, a 3D data set, where we collected simulated data on a sphere, distorted it randomly, and put it in with the correct constraints. And now the task of the algorithm is actually try to find this minimum energy configuration. And this is actually what is happening like during these optimization processes. And by the fact that it looks like a sphere, you can actually guess that we are very, very close to the optimum. But with this, you can build now really like highly accurate and complex maps. As I mentioned, like cell phone companies use this for optimizing entire like maps of cities and countries. Here is just the Freiburg campus. This is the building my group is in down here. This has been recorded with a quadrotor and a laser scanner attached to it. So we flew over our campus and created this data set. And this is super useful for a variety of applications, for example, in particular also self-driving cars. And here's one example that I want to point to, is that what is called valet parking. This is a project that my students, me and Sebastian Tran, one of the winner of the DARPA Grand Challenge, did in, I think, 6 years ago, about where we actually asked the question, can we use this type of technology for providing self-parking to self-driving cars. Right? So until then, cars mostly relied on the GPS system in order to navigate around in the Grand Challenge as well as in the Urban Challenge. And they follow GPS traces. When you go into parking structures, there's typically not enough accuracy in the GPS signal to allow you to accurately navigate around. So what we basically did is we created this map of the Stanford parking garage, which is approximately 260 megabytes in this version. It's a multi-story building. By aligning this map with the GPS, with the GPS coordinate of the real structure, we actually could convert every path we took in the building into a true GPS position. So what we basically did then is we took the car to the entrance of this building and gave it a target location over here. We could use this map for planning a path of the vehicle like up the ramps in the parking structure. And all we needed to do is then actually provide the car with the localization estimate in GPS coordinates from our localization system. And this was basically, we cut the wire to the real GPS and plugged in our localization system. And then the car was able to autonomously navigate in this parking structure. The long-term vision of this is whenever you go to a party place or a nice restaurant and it's raining outside, you do not want to walk through the rain, and you jump out of your car in front of the restaurant. You have an additional button on your car key that says park yourself, and then the car disappears and parks itself. We didn't solve the problem of getting the car back. That's another student project for the future. But here's the experiment. So this is Dirk Handel, one of my students at that time who did this project. He was working with Sebastian. He's now working at Waymo on self-driving cars. And he's sitting behind the steering wheel, and you see on a Sunday morning, like this car moving through the parking structure. The blue lines here indicate so it has a Velodyne laser scanner on the roof. We used one plane of this for localizing the car in this triangle map that you see here, and calculating the GPS position from that. That was sent to the path planning and control system, which then generated the motion commands. Actually, the car didn't know exactly about the height. It actually just followed this trajectory that in the vertical projection looked like doing several loops, but was actually just a sequence of positions it was supposed to achieve. Yeah, and then in the end, it moved to the rooftop and then like performed a dedicated parking maneuver to go into the right pocket. So this is basically what happened at that time. So this is basically what you can achieve with this type of technology. So you actually do provide systems with the maps needed for accurate and precise localization. All right, so from that point of view, you could also say robust mapping is something that has been partly solved. And as you can imagine, we are now getting closer to the summit of that mountain, right? Still carrying that big boulder. So there is another problem there, which is what is called long-term autonomy, or sometimes it's called lifelong mapping. And this is actually a little bit more complicated, this problem. And I just, to indicate the hardness of this, all I want to do is I want to briefly talk about one project, European project that we did. So it's actually a sequence of two projects, Europa and Europa 2, both short for European Pedestrian Assistant. And the goal of this was to build a robot that can navigate through a city center and perform all kinds of duties over there, for example, delivery or even surveillance or whatever you can imagine a robot in a city center would do. It could also be do cleaning. But for that, the robot needs to be able to do this over actually long periods of time. You do not want to follow the robot every now and then. So when you go to a real city, and Freiburg also has very, very interesting parts where it can be arbitrarily complicated. So Freiburg is well known for these tiny little canals that were used for waste removal in the mid-ages. So I cannot believe how much it must have smelled at that time. But nowadays it's beautiful. So kids play there in the summer, and you get cool feet. But for robots, it's particularly difficult because, robots and water are not really compatible. And so the robots cannot cross those canals, but there are like wheelchair access areas where we have gutters over those. And gutters are particularly hard for light-based sensors because gutters are like something you can actually look through mostly. So we needed to implement a dedicated classifier for finding those gutters, allowing the robot to cross these canals. And another challenge is kids, and this is one of my famous movies. So this is what happened when we took Obelix, that's the name of this robot, close to the city center. And this was typically surrounded by kids trying to play around with this robot. And in this case, there was an ice cafe. We could only resolve this problem by inviting all the kids to the ice cafe. And then the robot could continue afterwards. But we do know it's not going to work in the long term because it's going to put the wrong reward signal to the kids. So we will need to see. And so that was an interesting endeavor. And out of this came actually 2 or 3 startups that tried to build these type of robots for cities level navigation, for example, for pizza delivery or sushi delivery, particularly in places where it's enormously crowded. And so there's one startup in San Francisco and another one, I think, in Poland, that are actually trying to build robots that do exactly this. The funny story about this was that it's actually a couple of years ago, almost 6 years, or a little bit more than 6 years. It was on August 21, I think, 2012, where we decided, okay, we're going to make a field trial today and start the robot on our campus, which is 3.5 kilometers away from the city center of Freiburg. We give it a start location in the city center and let it go. And unfortunately, or fortunately, depends on how you see it, our press office had got to know about it, and they had informed the press. And on that day, August 21, we had 20 press teams waiting in front of our campus, watching the robot to fail, or trying that was their intent, actually. So this is like footage of the robot on that day. You can see real camera footage, camera people. The story made it to like virtually every news. Newspaper on the next day, on the front page of every German newspaper. We also got into all the major channels in the evening, like news and TV. My famous one is, so this is the path the robot took. The robot actually made it. These were the people mostly in charge of it, Bastian, Rainer, and Michael. So this was a press at that time, very same moment. But we made it into Channel 1 of Germany in the so-called Tagesthemen report. It's a major news, one of the major news, what is it, how it's called, shows in Germany. We also made it to the Tagesschau with the 8 p.m. one, like 50% of all Germans watch that. I always thought, like when I make it into one of those, I'm going to stop doing research. I'm done. So here is the report. It's 3 minutes long, and I'll let you wait. So this is why it's called Obelix, the robot, or this is why they took this picture. So my students, we did a doodle poll at that time, and my students thought that the form of the robot is like indicates that it should be named like this guy. I don't know whether it's actually admissible to call someone Obelix, but I guess so. So the Tagesthemen guy, Tom Burrow, made a report. It's in German, but I dubbed it in English. So for those of you who know a little bit of German, it's now time to practice again, and all the others can read the subtitles.
Seitdem der Gallier Obelix als Kind in einen Kessel mit Zaubertrank gefallen ist, ist er wahnsinnig stark. Er bahnt sich jeden Weg, selbst eine Legion Römer kann ihn nicht aufhalten. Dabei bleibt das Schwergewicht aber etwas tollpatschig. Sein Namensvetter ist ein nur 100 Kilo schwerer Roboter, der heute in Freiburg seinen ersten Spaziergang absolvierte, ganz ohne fremde Hilfe und egal welche Hürde im Weg stand. Auf diese ersten Schritte hatten Forscher mehrerer Universitäten Obelix 3 Jahre lang vorbereitet. Florian Gedin berichtet.
Fast sieht das hier ja aus wie eine kleine Prozession. Und es hatte auch durchaus etwas Feierliches, diese Weltpremiere heute in Freiburg. Die Jungfernfahrt dieses eigenartigen Geräts, das sich wie ein Gast aus der Zukunft unters Volk gemischt hatte.
Ein Roboter, echt?
Obelix heißt das Gerät, ja. Und was will man mit dem bezwecken, das würde mich mal interessieren.
Der Zweck des Ganzen war heute eine Art öffentliche Testfahrt. Es ging um die Antwort auf die Frage, ob Roboter Obelix eine belebte Innenstadt ohne Hilfe durchqueren kann. Das wollten die Forscher der Uni Freiburg herausfinden.
Wir hoffen, dass er irgendwann mal tatsächlich die Städte bevölkert oder solche Roboter die Städte bevölkern, so wie wir Menschen das auch tun und dann eben halt autonom Dienste ausführen, Botengänge für uns ausführen und so. He couldn't pass me, that's why he's
4 Kilometer Teststrecke und bitteschön unfallfrei durchs Straßengewirr. Das war heute Obelix' Aufgabe. Vom Stadtrand hinein ins Zentrum der Altstadt. Dabei jedes Hindernis erkennen und umfahren und die vielen kleinen Gemeinheiten der Großstadt überwinden. 3 Jahre lang hat es gedauert, etwa 6 Millionen Euro hat es gekostet, bis der Roboter reif war für die Rundfahrt durch unseren Alltag. Doch trotz feinster Technik zeigte Obelix sich hier und da noch etwas zickig.
Ja, also er nimmt diese Mülltonne da jetzt über seine 3D-Sensoren wahr. Das wird jetzt sehr, sehr eng, wie Sie sehen. Ich bin auch ein bisschen nervös. Ne? Der Bordstein ist auch relativ nah. Warum er jetzt anhält, weiß ich nicht genau. Vielleicht ist es ihm ein bisschen zu eng geworden. Wir müssen gleich mal schauen. Aber ich bin immer noch guter Hoffnung, dass das jetzt gleich noch weitergehen wird.
Richtig festgefahren
so we had
und
actually
reif für Diagnose.
two cases where the robot got stuck. One was in the middle, in front of our rectorate, because it's a wide open space, like with only trees, and unfortunately people surrounding a robot look like trees. So the robot actually got confused about like where it was, and because the sidewalk is only 1.5 meters wide there, the robot actually got too uncertain. There's the advantage of this probabilistic formulation, like the uncertainty got too high, and we had programmed if it grows too big, then the robot actually stops, and we like provided with the correct location in order to continue. So this was one of the cases. The other one was a journalist running into the emergency stop. So this was one of the experiments that we did. And as you can imagine, if you want to build a real robot in the real world, then you have to deal with environments like this. And this is what these companies, all self-driving car companies are currently working with. In principle, we understand how to do navigation and how to get from A to B. But there are so many, that is what is called corner cases, which take an enormous amount of time. So the car companies the best ones are right now at approximately 5,000 miles without critical intervention. So we had 2 on the 3.6 kilometers, so to say. So we have 1.8. Right? The car companies are at approximately 5,000. In order to be competitive with a human, we need to reach 50,000. So a factor of 10. And then the question is, how can we achieve this? And this is actually what we are. What leads me to the second half, or not half, third of this talk. actually where we are going to talk about what can we do next. And like remember, right, close to the top, not at the end of this talk, but to the top of this hill. And all of a sudden, like, we discover, like, we have worked for 20 years on this, and can we solve this, or do we need to take another approach to maybe get even further up? So that's what we are doing in science, typically. Right? We're coming up with a new idea that can make us, or take us maybe further up the hill. Right? And so the idea is right now, and this is what is happening in all over the world, is basically using machine learning for solving this task. And I want to give a few examples where I think this approach of combining robotics with AI technology, and in particular machine learning, will provide us like with the necessary adaptivity of such systems to cope with more corner cases than we can manually program. So this is the basic idea of this. And so, for example, look at this problem of learning driving styles. Emanuele and me had this discussion when we walked through Padua half an hour ago, that it is extremely hard to adjust a car to the preferences of a user. And also to adjust a car to different environments. As you might imagine, like, cars move differently in Southern California than in Padua or Palermo or Tehran or New Delhi, right? It's going to be a completely different type of driving. And what needs to be done is that these cars actually need to be able to adapt to the specific styles of human driving. And in addition, what you would like to avoid is that autonomous cars are identified as autonomous cars. We have seen, and this is going to be something that we can expect, that we have seen those kids challenging robots, and this very same is going to happen with adults in traffic. Autonomous cars are going to be challenged. And this is why it is actually important to build cars that cannot be identified as easily as being self-driving. And I want to go quickly to one, so this is, so let's skip this as well, or maybe go back in a second to this. And this is an approach that I've been working on with Nicola for a couple of years. It's basically on this question of learning user preferences. And this is an interesting problem. If you think, for example, that in the long run, we are going to be able to buy service robots from a Home Depot store. So we go into a shop, buy a robot, unpack it, and then, exactly what then? Right? We are going to tell it, so please clean up my kitchen table. Right? Okay, this is also a very, very precise text. Right? Maybe the robot is going to be able to understand it, but it's extremely hard to implement it. Because it might be different, like you might have a different opinion what a clean kitchen might be than I. Typically, my students are less accurate about that than I am. Right? And I'm also less accurate than my wife. But this is something, yeah. So there are always kind of discrepancies. And so, which means that robots need to learn and maybe adapt to their users. And it's an interesting question. And also, for example, think about the question if the robot actually sees salt on the table, where should it put the salt? Where should the salt go? And in fact, you could go and instruct it for every object where to put it. But this is not really something that you would like to do. In addition, you do not want to tell the robot every morning, now please clean up the kitchen table. Maybe you just want to leave, and the robot sits there around and says, you didn't say anything. You're not going to be happy about this. So the robot actually should be able to infer what you want. And so we need to have robots that are able to adapt to their users. And the idea of this project was using techniques from recommender systems to infer what people actually want from the robot and to infer where they want the robot to put things. And the interesting part is you combine this with crowdsourcing. So that's what we did in this project. We basically asked people over the internet to tell us, we showed them a shelf, and we showed them objects, and we asked them, where would you put this object? And based on this, you can use these recommender system technology, which is basically the very same when you go to your favorite online store. Usually, after you bought something, there's this line in the very bottom that says, people who bought this also bought that. And this is exactly the very same thing. So people who put the salt over here, put the pepper over there. Right? And this is basically the technology that we use for this. And this is interesting. So if you watch that video, so this is on the left-hand side, is that what the robot actually sees? And the blue boxes are the predictions about where the robot would put the other things. And when you now go ahead and move things around, then, for example, put the rice to the other side, then it puts the other things to the top. And then depending on how you arrange this, it actually reconfigures the entire shelf. And the idea there is that the robot can actually learn how you want to arrange your shelf. And the interesting aspect is that comes as a prior. And once you showed this often enough or with a substantial weight, then the robot can adapt to yourself and also have this as a crowdsourcing aspect, put this into the big database and maybe enhance that recommender system technology in order to get better predictions about where things should go. And we also did something similar. We used something like that in the context of these of our excellence cluster project. I don't know whether this video, where we do have that's what we call brain-controlled robots. It's brain links, brain tools. So a cluster of excellence that we are running, and there we are interested in building robots that can be controlled via brain-machine interfaces. And over these interfaces, you have an enormously low bandwidth. And this is why we actually need to have adaptive and autonomy techniques for autonomy in order to being able to actually robustly serve people. And this is an interface where the person actually selects a task of the robot to be carried out. And then in the end, it's going to be like a feeding task. So get me a drink. And then from that, the robot infers where the bottle is, opens the bottle, does everything autonomously instead of basically using the autonomy of the robot to cope with low bandwidth interfaces for establishing complex services to users with impairments. Yeah, sorry for the cables. The latest demo runs without cables there. Right? But here the robot actually gets to a table, pours the liquid into a cup, and then goes to the patient and feeds the patient. In this case, a student. And we also worked on filling cups with water, which is also an interesting research problem. And yeah. So okay, I think time is running out. I need to hurry up a little bit, but it's not much more that is going to come. The next step, and that is what has happened in robotics over the past years and will continue. Last year, we had to establish a dedicated keyword called deep learning and robotics. And there are almost 5% of all the papers were submitted to this particular keyword that came out of nothing, and which is deep learning, and it's going to revolution robotics as well. So there's going to be a tremendous hype right now on deep learning technology, and this is relevant for various aspects like object recognition, people detection, and so on, and also navigation. And here's one network that we used just to give you the intuition about what you can actually achieve using these type of networks. This is a fusion network for RGB and depth. But what you can, by choosing proper architectures, you can actually achieve performances that go beyond what we had seen before. This is not the latest result. There are 20 or 30 more approaches right now that outperform what we have done a few years ago. And we also applied this for human part discovery, which is enormously relevant for robots in public spaces. So the architecture here, it's actually pixel to pixel. You basically label every pixel in the image with a pixel on the right-hand side saying which part of the body that is. This is super relevant for disaster robotics, for example, but also robots operating in the real world. And this is original Obelix footage, a short sequence of images with the corresponding labels that we got out of these deep networks. And there's also an interesting project that we did about sound classification. So this is video footage of a robot with a microphone, and what you hear is the sound of the tires interacting with the ground. And maybe when you drive your car in winter, right, then you often are able to identify as to whether you are on asphalt or on snow, right, just from the sound. Right? So the idea there was to basically listen to your tires, was that what I would call these projects, trying to identify the type of terrain you're on based on the sound that your tires make. And for that, we developed a dedicated network that is able to actually deal with time series. So it's a little bit different. This is a robot that we used. We used this type of microphone. It's 250 euro. Later on, we just duct taped a cell phone underneath the robot and used the microphone, the cell phone microphone, for doing this. And so these were the type of surfaces that we considered. And the interesting part is that with that, we can actually distinguish between grass and mowed grass. So if you have an autonomous lawnmower, you could actually use this approach to figure out as to whether the robot has been there or not. And here are the comparisons with the most sophisticated approaches. Like in the end, we compared with the Capstra approach, which was the most advanced technique for sound classification. And this is the result that we obtained with the deep network. And if you increase the time window, then you even get to 99.4%. So there is a web page Abhinav, my student, set up for this project where you actually can go and listen to the sound clips and try to classify them yourself. The current average performance of humans is 25%, right? So, but I mean, I guess that over time, like when you practice a lot, then you will also get substantially better. But I mean, what people achieve with these type of technologies is that what is called superhuman performance right now. And this is why there is a chance that we actually, why I believe that at least in some cases we are going to be able to reach a level where we can actually hit this 50,000 miles and build the truly autonomous cars. And yeah, so there are other examples, terrain classification, just to, like based on images, like in trail, grass, vegetation, sky, super relevant for auto navigation vehicles. And also there's also interesting using a monocular camera to distinguish standing from moving cars from a moving car. So you have one camera, one dashboard camera, and you actually want to know as to whether the vehicle in front of you is moving or not. This is also highly important for self-driving cars because you always want to know as to whether a car is like pulling out of the parking spot or not, out of the pocket or not. Red means behind max range. Right. Two different approaches, but finally, I just want to get to this problem of that what is called navigation. This was mostly perception, what I talked about. These are my final slides now, and this question as to whether we can actually also do end-to-end navigation. So can we build a network that performs navigation autonomously? And the very first approach that we tried, and I find this very impressive, that is why I show this here, is treating navigation as a classification problem. In principle, what you would like to do is you would like to take your most recent observations that you had, and from that generate the next motion command that you want to give to the robot. So imagine that the robot starts in this blue dot over here and needs to go to the green dot. In this environment, red obstacles, black free space. In this case, this is the top level view of the robot. So it's kind of like this window over here. So this is what the robot actually sees. And now imagine that the robot observes a sequence of such observations, okay, of that window, of such windows. The question now is like, what is the next best action to take in order to get to the green dot? And this is a supervised learning problem. You basically provide it with a sequence of actions. If you know the optimal path, you can calculate the optimal path. You get the sequence of observations that tell the robot how to get into the target location. And you can also train a deep learning algorithm, in this case, a random forest, for example, to perform exactly this task. And it turns out it performs amazingly well. So basically, the interesting part here is now that, I showed you in the very beginning that the robots need a map to localize. Once you know where you are, you can use a path planning algorithm to get from A to B. But this deep architecture now doesn't have a map anymore. It also doesn't know where it is. Right? It just learned what to do from its sequence of observations that it has. So that means that you can perform navigation somehow without localization and without path planning. So two important components. It's kind of localization and control. They're now gone out of these three bubbles that we had. Right? So what is missing now is mapping. So in order to train, the system actually needs a map. And so this is what we also looked into. It works also with different sensors. So that's what we also looked into. Like, can we also do SLAM with these type of deep architectures? And in this case, deep reinforcement learning architectures. And this slide wouldn't be here again, right? If the answer is no. So there's math behind it, right? But so this is the interesting chart here. So the red line here is basically, so the goal of this is, we cannot do this in random environments, but let's assume environments look not too different from each other. Think about supermarkets that all have a similar structure. Right? Can we learn efficient navigation in one supermarket once we have seen other supermarkets? So what the robot actually needs to do is it needs to transfer that what it has learned from these previously seen environments to the new environment. Red line is the optimal path calculated under the assumption that the robot actually has the map and can calculate the optimal path, A star. The green line is that what we have seen before, this system that learns from the A star paths, the optimal action. And that what we have, this algorithm that we have, or Jingwei, my student, has implemented is supervised reinforcement learning with task transfer. That's how it's called. It's this cyan line over here, or magenta line over here, that basically gets very, very close to the supervised approach, which means that these robots can transfer their navigation capabilities very, very quickly from one environment to the next, which means, and without building an explicit map, which means that in the end, we can do something like or implement the complete navigation pipeline without doing all the stuff that we have seen in the first 60% of this talk. So here's a demo about this. It's just robot moving around, just to give you the impression that we also implemented this on a real robot. So here the robot actually moves around and learns from one environment when we move the target location and also the obstacles, and is able to transfer this to a new environment. And, the key question now is like what this actually means, right? The outlook might be that just based on these learning methods, we can actually implement things for which we previously needed a lot amount of modeling and programming effort. So it could be that in the long run, we enter a field of robotics where we do not need to program anymore. Once we are perfect with these deep learning, or we understand all these deep learning architectures and how to use them for real-world applications, and then also that might ask the question, what is going to happen to this book that my colleagues and me wrote in the past? And one view of this actually is that at some point in time, it's completely replaceable by that what is called deep learning. And in the end, we don't need this anymore. There's no math we need to study anymore, just scripting deep networks. And which brings us to the end of this talk. Right? The boulder's on the ground right now, and we can actually start carrying up the hill. Thank you.
Okay, Wolfram, thank you very much for this inspiring talk. But I feel very emotional because the work he presented are the basis also for the work I did in this year, and so I really appreciate that Wolfram was here to share with us, and so also I wanted to share this personal feeling and this personal thanks. So we can take some questions from the audience. I would be happy if there are some questions.
Yeah.
I'm working on microelectronics part, so sensors and devices. So I was just asking which are the particular sensor you may have in your device, specific feature, I don't know, motion, infrared or ultraviolet, I don't know. Any kind of, is it very complex or just use camera and little more?
So what we are using mostly is cameras and also laser scanners, and they work in infrared. But they are also, like, infrared has the disadvantage of being very, very sensitive to water and snow, fog. So there are other wavelengths that they are exploring right now. I think green lasers are better when it comes to fog and so on. This is also the reason why all these self-driving car companies are in California, because there's virtually never bad weather.
Sunny.
Yeah.
Okay. Yes, Matteo.
Thanks for the very interesting talk. So I have a question about what you see as the future of deep learning. So you talked about transfer learning, so transfer the abilities that you can learn from a data set also to another task maybe. What do you see in the future? Are we going to build new type of nets, or are we going to have a standardized type or set of nets that we can use just fine-tuning them for new tasks?
I think it's going to be like to a large fraction, we're going to use established architectures and maybe use them for these tasks. And of course, you can always try to improve the results by like changing the architecture as well. And this is a little bit of a piece of art that people are able to do, like figuring out what proper architectures are. There are very, very interesting developments right now that people, for example, there's been recently a paper where people try to embed the particle filter algorithm that I showed in a deep network. So it's called differentiable particle filters. So you can actually also optimize the particle filter algorithm, like the sensor models and so on and so forth, while performing localization with these type of networks. And this is very, very interesting, because then all of a sudden you end up being in a regime where you can automatically optimize processes. So I cannot tell exactly, but one also needs to be, I mean, I was a little bit provocative at the very end, right? I think that modeling still has its role. And I mean, usually the best you can do is model it as much as you can, and then for the rest, for the remaining part, use machine learning. Like, I mean, models are always wrong. That's something that is also for sure. And usually you need to have something on top of models to learn this delta, to learn the deviations. And this is where these, like in this combination, we can get enormously far. And they have been super successful in perception, because with perception you cannot harm someone. It's different when you go to autonomous cars, when you actually have to like move a ton around, then you need to know more about systems and what is going on in the system.
I have a question on this concept of modeling with respect to deep learning. In some sense, deep learning is coupling directly perception to action. No? You showed some example. And for those of us who studied robotics, we are used to the robot is working with the loop perception, reason, and plan, sense, plan, act loop in which you perform the action. So one term that was very successful in the 90s was symbol grounding. No? The fact that you can reason about things in a mathematical model with formal logic or whatever, but in the end, for robots, it's important that these symbols are grounded to the real physics of the environment, to the real meaning of the environment. And somehow all this discussion disappear in deep learning, because the perception is directly linked or related to the action without any modeling of the world, without any understanding, if you want, of the world. Yeah. And I'm a bit concerned, because there are experiments from colleagues from Stanford, I suppose, about that make experiment by putting simple stickers on traffic sign. And so just by modifying a little bit the pattern of a stop sign, but a human driver will see that it's a stop sign, an autonomous car using deep learning to detect, to understand, it's not understand, it's detect traffic sign, will classify the stop sign as a 50 kilometer speed limit, so we'll cross the junction at 50 kilometers per hour. And this is because you are losing the symbol grounding or the modeling of the world. So can you comment? What's your feeling on this?
Yeah, I mean, this is a super important aspect of this. First of all, I mean, what came to my mind in the first place was actually, I mean, we live here we are here in a very, very historic environment, and this is also something that need to remark in this context, that actually was played a major role in figuring out the physics. And I mean, Galileo was also someone who actually looked at how the world actually works. And but still, and it took the society. You now might ask the question, like, how long did it take us to figure out finally that what Newton wrote down with Newton's laws? But still, we were able to conduct these experiments. We were able to make predictions about what is going to happen, and we were able to hunt animal by throwing spears at them. And if you ask someone, if you go to the street and ask someone, so can you please write down the equations, how to actually, when you want to throw a stone or a rock over that river, virtually nobody is going to be able to do this. Still, everyone can throw a rock over the river or into the river. So which means that there are beings in the world that can exist without bottles. And thus far, Newton's law has not been found in any of the brains. So this is one the first answer to that. The other one is, of course, that there are these adversarial situations which are super critical, but my belief is that this also happens to humans, right? We can all have installed things that produce optical illusions or prevent us from identifying things or seeing things. We engineer the world in a particular way that we can see things. And this has all been done for us, and these traffic signs are made in a way that we can easily see them. I think this is a major problem, and we somehow need to solve this. I think it's good that there still is some research. I didn't say that with this attempt we're going to bring the boulder to the summit. I do not know what's going to be after deep networks, but we are going to be busy for quite some time with that, understanding the full potential and also the limits.
Thank you. Oh, yeah, Alberto.
Well, again, thank you for the speak. And my question is similar to the last question. It's about data. Data you need to teach this network, and of course they work pretty well when you have to classify, suppose, brands or other objects. And huge companies like Facebook and Google are provided with huge amount of data, but more the problem is complex that you want to solve with learning, with deep learning. More the data you need is complex to collect. And also, if you want to simulate data, is a high expensive task, because you can use video games as many approach that try to do localization, but video games cost tens of millions of dollars to be developed. So it's a big issue, from my opinion, the data you need to make it works properly, this system.
Yeah, I completely agree, and also simulation will not entirely help us, because once you are able to develop a proper simulator, you solve the problem. And then, and the other aspect is true as well, but there is some evidence, for example, or some companies are going into a direction. If you look at, for example, all the taxi services. The problem right now is that some companies are trying to do this in a top-down fashion. They're basically trying to develop it and having it ready for the market. What they do not exploit is the fact that you could actually take those cars when they are driven by humans and use all this data for learning. So I think that the opportunity for learning from human demonstrations in the context of self-driving cars is not fully exploited. And this is something where I believe, and there are companies, particularly that when you look at the Chinese market, there are companies like, for example, Didi, that has more taxi rides than every other taxi service in the world, or all them together. And they're probably going to have way more cars on the road. And you can use those for data collection. I think they are planning to have 60,000 cars or so. And then all of a sudden, you get into a dimension where you might have enough data for learning robust policies on these cars.
I'd like to ask, which are the frame rates commonly required by these algorithms to perform a good motion, autonomous motion?
Yeah, I would say this is not good autonomous motion, right? You mean like the deep learning architectures, that there we are far away, but the other ones, like with the city navigation robots, kind of like 4 hertz is something like that you need for issuing control. Okay. I mean, localization is like something like in the area of 1 hertz. I mean, of course, when you need to have fine-grained localization is maybe, I don't know, I would need to ask my students, but my guess is between 5 and 10 hertz for like interpreting the laser data.
Okay, thank you.
Yes.
People are warming up now. Yeah, let's do the last one.
Yes, just a short one. What about sensors, the sensing part of the system, and the possibility of aging of sensors, of deviations in performances, reliability of the sensors? Yeah. It will change perception, so how it will behave?
Yeah, that's a super important question, and also the dependency with respect to weather. And but there are also approaches where you can actually perform data fusion with these type of network architectures. And the interesting part is that, at least to my experience, that in these networks you can actually have them configured in the way that they by themselves decide upon the most reliable data source. And I mean, in fact, these systems need to have seen aging sensors. And once you have this, then if you are in a learning approach or in a learning regime, then you need to have these type of data beforehand. And then I think you can at least deal with such situations.
Okay, so thank you very much to everyone. I would like to close this section, and I would
thank you for coming.
No, okay, thank you very much to Professor Burgard, and also to the audience for the nice questions.